Okay, I'd like to preface this by saying some of the work I'm going to talk about was done with my colleague and friend Ron Lehman. I do, however, demand full credit for any mistakes. Okay, I should note that the question that I ask in the title of my talk has already been answered very nicely in the words of Che Guevara in the musical Evita. The answer is a qualified yes. Despite its age, the universal gravitational constant G, it's the second, in my view, the second oldest. Romer's measurement of the speed of light antedates the publication of the Principia. It is the least well measured of the standard physical constants. The current value is 6, right? You can see it with a fractional uncertainty of 2.2 times 10 to the minus 5. You can compare it to, say, the G factor of the electron, which is among the best measured, which is 1.72 times 10 to the minus 13. Now, if we look at contemporary measurements, this I got from CODATA, you might question as to whether there is a gravitational constant. This is, I think, the 2014. The values are all over the place and they do not agree. In fact, at this point, the CODATA suggested that they expand the uncertainties by a factor of 6 to get a decent chi-squared to the measurement. There's some interesting points measured here. This measurement by Quinn et al. Actually used the same apparatus, but two different ways of measuring it. They used the standard kind of Cavendish torsion balance, determining the constant by the period of the free oscillation. And they also measured the electrostatic force needed to just hold the balance in place. This is the most precise measurement by Gunlach and Merkowitz. Now, it's interesting, you talk about precision. This is 40 parts per million, this is 14, but they differ by 200 parts per million. So there is a question about what it is. Are they measuring the same thing? Or whether or not there are other effects. Now, there are possible reasons for this discord. The gravitational force is very weak. If you look at the hydrogen atom, the electrostatic force between the electron and proton in the ground state is 2 times 10 to the 39 times the gravitational force between them. The gravitational constant G is not tied to any other constants like the fine structure constant, which depends on the value of E, the fundamental unit of charge, H, and C. So there are no constraints. And also, and I think this may enter into it, you can't shield the gravitational force. That if you look at Cavendish's original experiment, he is worried about the effect on his torsional pendulum of other parts of the apparatus, which you might not need, the walls. Okay, now there is in fact a long history of discord in measurements of gravity. If you look from the early 18th century to the late 19th century, when they measured the density of the Earth from which you can get the gravitational constant, it varies from 4.25 to 7.6, where 1 is the density of water. And often, interestingly, the data is analyzed not only by the author, but by others. and then published, you get some very funny results. There are even some experiments reported in the 1770s that argue that the inverse square law is wrong, that in fact the gravitational force increases as the square of the distance. This was done by Father Berthier and others. The results turned out to be fraudulent. He inveighed against people who invented laws to make God. Of course, he had no evidence. And I quote Christopher Hitchens, who says that which can be asserted without evidence can be dismissed without evidence. This might be appropriate for recent political thought in the US. Okay. Now, what's interesting is that comparative measurements of gravity, however, are much more precise than single or direct measurements of gravity. If we look at, for example, Galileo's measurements of the fall of two bodies, you can estimate it as about a part in 500, depend on how you define a hand's breadth. Newton claimed a part in 1,000 by his experiments on pendula with different materials. Bessel got a part in 60,000. Etvosh got a part in 10 to the 9th. And Etwash, where Nora knows more than I do, they measure the Etvosh parameter, which is the ratio of gravitational to inertial mass for two different substances. If you subtract it, divided by their sum, you get a part in 10 to the 13th. Now, one might suspect that this is because in these cases, when you're looking at the equality of fall, the universality of free fall, the systematic effects tend to be the same for both. But in the Etwash experiment, they in fact do even better. They transform systematic effects into measurable or calculatable systematic numerical results, which they correct their value for. For example, with tilt, what they do is they tilt the apparatus a fair amount and see what effect they get, and then extrapolate it back to their original apparatus where they know how much tilt they could have. And so they make corrections rather than give the uncertainty. They do have, of course, an uncertainty associated with these. Okay, now, G is not the only constant that has a checkered history. There are others which are perhaps less obvious. And I'd like to talk a little bit about the work of Raymond Birge at Berkeley, who from the late 1920s through to the 1950s was regarded as the arbiter of fundamental constants, at least in the US. He made judgments of the quality of measurements and set the best values. And he defined what became known as the Birge Ratio. It was the ratio of the external uncertainties, i.e., between different experiments, and the internal consistency of a single experiment. And he says that when that ratio exceeds 1 by an amount much greater than is to be expected, one has evidence of the presence of systematic errors. And in fact, he rejected a huge work on atomic masses by Clark because the Birge ratio was 10. He never quite specifies what that ratio was. Now, one thing about Birge is that he tended to like measurements made by American physicists whose last names begin with M. He, for example, talks about, he mentions that it's highly desirable that a measurement of a quantity should be made in different ways, but he says only one really precision measurement for the value of E is known, and it was carried out by a single individual. And a masterpiece of experimental technique. And this is Robert Millikan. In the question, I'll point out that Millikan's data analysis is subject to some question. Birge also liked measurements of the speed of light by Michelson. It surpasses in accuracy any of the preceding that need to be considered. This is him in 1929. Now, Birge's work, he published every so often tables of these things. He was criticized by Frank Benford, who pointed out that between 1929 and 1941, the velocity of light changed by 5 times the quoted probable error. The electronic charge changed by 6.5. Planck's constant was even worse. It was 9.6 times. And the odds of those things happening, if those are real probable errors, was very small. And he was, shall we say, polite, but quite critical. He said the depth of credit chemists and physicists to Dr. Birge is great, and I hope that he will in future lists increase this indebtedness by pointing out the distinction between consistency and accuracy. Now, Birge pointed out correctly, I think, that he had in fact done so. This I feel. He says he's done this because he talks about the Birge ratio, which is exactly the distinction between consistency and accuracy. And he says you can only determine the difference between internal and external. The true value of any magnitude can never be known. Now, what's interesting is if we look at, he's not worried, particularly, by the way, about the idea of a constant. He says, it's okay if it changes. There's no problem about it. He expects it. If you look at Millikan's values, that from 1911, it goes to 1917, it goes from 4.891 times 10 to the minus 10 to 4.774. The 1913 and 1917 happened to agree. But notice the viscosity of air changes dramatically between 1911 and 1913. Millikan made no mention of this in his 1913 paper. In fact, if it was an effect of the viscosity, the value of E should have increased. In Millikan's experiment, the value of E goes as the viscosity of air to the 3/2 power. Millikan attributed the lowering of the result to improvements in his optics of his experiment. Okay, so Millikan's results were perhaps less beautiful than Birge said. Here we have values of the speed of light. This is from a paper by Henrion and Bischoff in 1986. They show the values changing as a function of time. In the period, they note from 1876 to 1902, compared to the modern value, C was overestimated by about 70, kilometers per second on average from 1905 to 1950. It was underestimated by 15 kilometers per second. This led Birge to conclude that the speed of light was decreasing by 4 kilometers per second per year, and that in 75,000 years, the speed of light would be 0. And of course, at that point, you might call it the speed of dark. Okay, now, the question one asks is, should experimenters increase their stated uncertainty to allow for problems with systematic uncertainties? Now, Cohen and Dumont, who took over for Birge, they were at the National Bureau of Standards, say no, that you shouldn't enlarge your errors to take advantage. Systematic errors do not obey any known statistics, and you do the best you can. It's a kind of heroic view of experiment. Now, one of the problems with unknown systematic errors is that they're unknown. How large a factor should you increase it by to take account of unknown errors? I was once asked this at a conference on the fifth force. Somebody said, well, shouldn't we increase our uncertainty by a factor of 2? I said, why? Why not 3 or 4, since you don't know the size of any of these effects? Okay, now, Birge worried about another effect. This is the idea of the bandwagon. He attributed the quote to Ernest Lawrence idea, the experiment that does an experiment, he looks for sources of errors and continues to search for them until he gets a result in agreement with the accepted value and then stops. You then get a value, and okay. So, and this bandwagon effect is a real possibility. As I will show you both. This is I refer to this graph as the peculiar history of eta plus minus. I don't call it the strange history because the K meson is a strange particle. And up until 1973, that was presumably well measured, had a mean of 1.95 plus or minus 0.03. After 1973, it was measured very nicely, except that it was 2.27 plus or minus 0.03. And in a paper I wrote back in the old days, I said this was a surprising change. And the referee said, no, it's not surprising. The later ones are just better. I want to bet with this guy because the chances of an H sigma thing is like 1 part in 10 to the 15th. Now, this may be, by the way, for those of you, the philosophically minded, this is maybe the first observation of a GRU quantity. The current value, by the way, is 2.23 plus or minus 0.11. And this discrepancy was noted by the particle data group. They say, yeah, we could average it and get 2.15, but we'd have to put in a scale factor. They had a way of estimating the scale factor by what would give a reasonable chi-squared. And this came up in the question of Nora's talk. They said, no, the newer experiments are in principle superior. higher statistics, acceptance, easier, truer. They've chosen to average them separately. Now, I know something personally about those first two 1973 type measurements. The first was done by a group at CERN headed by Jack Steinberger. And I wrote to him and said, well, why did you do it if it was already well measured? And he said, the reason they did it was they were actually wanted to measure the phase of eta plus minus, which was not well known. And you have to do an interference experiment, and essentially you get the amplitude for free. The second one was done by a group collaboration between Group G at SLAC and the University of Colorado. I was a member of the group that took all the data, but I was not involved in the analysis, so I was not an author. But the experiment was not designed to measure eta plus minus. But when we saw the preprint, in those days you actually got printed copies of a paper before we knew that we had 4,000 events and we could measure it also, and did. Okay. Now, if you look at, and this is a question one might ask, should particle masses be, here's a list of graph of showing particle masses as a function of time. These are world averages as computed by the particle data group. And you'll notice they change and then pretty much converge. This one was funny. This is the mass of the lambda particle, and it was claimed in the 1960s that you could tell when somebody got their degree by what mass they used for the lambda in their dissertation. And commenting on this, the particle data group says, sometimes there are large changes, but by and large, however, a full scan of our history plot shows progression toward greater precision at central values, quite consistent with the first data point shown. We conclude that the reliability of a combination of experimental data and our averaging procedures are usually good, but it is important to be aware that fluctuations outside errors can and do occur. So the answer is, yeah, they are constant. Now, in looking at this, thinking about physical constants, I looked at the code data and the particle data group. According to them, most recently, E, the fundamental unit of charge, Planck's constant, H, and C are all exact. Now, alpha, the fine structure constant, is 2 pi E squared over HC. But code data lists it as something with an uncertainty. Now, I don't quite understand this, because if E is a constant, is exact, which they list, H is exact, C is exact, 2 is well known to be exact, and pi can be calculated to whatever exactness. Why do they list it as something with an uncertainty? Perhaps they're listing, my guess is that it's because this is in fact the best measured value, if you will, but it is a puzzle to me as to why they are citing this if E, H, and C are all considered exact now. I noticed that 1 over alpha is getting very close to 1 over 137, which has been an interesting problem for people. Thank you.